All right, today, 7-5, spherical geometry. Spherical geometry, our learning goal.
Spherical. Isn't there
Logan,
H
you reading
in
the
that?
learning goal to Bethany? Yours? All right.
It says spherical geometry on ours.
Spherical geometry.
Yeah, spherical. Doesn't have an H.
Really?
Yeah.
Unbelievable. An H was forgotten in the note page you have there.
Sounds so
Okay.
confusing.
Our goal, using some of the basic ideas of spherical geometry. This is the only day we'll study, well, today and tomorrow we'll study spherical geometry. Understand that we live on a globe. Well, we don't live on a globe. We live on a sphere. Okay? When we look at a globe and think of our planet there, we're on a sphere. So spherical geometry has a lot of application. Okay? Columbus, all right, prior, like when they thought they were going to fall off the edge of the earth. Okay? However, we now know we live on a sphere, so spherical geometry. Okay? So we want to make sure that we're able to calculate. It's used a lot in travel, as we'll see tomorrow. We'll see some application of it, a little more application, but you'll also see it referenced as Euclidean geometry and non-Euclidean geometry. What we've been studying all year is Euclidean geometry. It's geometry on a flat surface, on a plane. Whereas spherical geometry is on a sphere. You may hear this as planar geometry, plane geometry. Okay? Spherical geometry is what we're studying today. Okay? So there are different ways that you're going to hear this. Euclidean, non-Euclidean, planar, spherical. Okay? Just kind of note the differences. Is it a serious question, Zach? Okay. Very good. All right. Right. So a few differences. The main goal today is to figure out the differences between Euclidean and spherical geometry. Euclidean geometry, like we said, exists on a plane, and remember, a plane goes on forever. A sphere is a finite surface. That's a big difference, and we'll might be one you add to your list when we go through this a little later. You have a point. You could have a point on a sphere. You could have a point on a plane. A line on a plane looks much different than a line on a sphere. Okay, and then obviously the plane surface is different. Infinite amount of space versus a finite amount of space. All right. If you look at page 340 of your textbook, you have that in front of you. I've made a copy of it. It's not an amazing copy, but the best known, a line on a sphere is called a great circle. Okay? A great circle would take and cut that sphere in half. Okay, now let me say that again, because some of you are going to get distracted here. A line on a sphere is a great circle. A great circle is what cuts that sphere in half. Okay, and we referenced this a bit when we talked about surface area and volume. Okay, but a great circle is what would cut that sphere in half. So what is the most popular great circle on our globe? Zach? Yeah, the equator. Okay, the equator is the most popular. Yeah.
Oh, I was going to say the next one was
Yeah, it's not quite as popular as the equator.
Yeah, I was going to say.
Everyone strives to every line on the globe strives to be the equator. But yeah, you're thinking the prime meridian. Yeah, I wish I could fit the globe under the document camera, but I cannot.
You can. Just lift it up.
Can you turn the document camera?
I could, but then what ends up happening is I have students staring at the document camera.
Do it
or
that way.
staring at each other.
Yeah.
Yeah, but then it's upside down. So if I attempt to do this, I don't want. No, see, here the problem is I'll get you guys on the picture and I can't have that. So we won't go there. We're not doing that.
So you don't want us to
People going like that. All right.
Nobody's looking.
So, in spherical geometry, the shortest distance between 2 points is the arc of a great circle. And you can make an infinite number of great circles. Okay? The one that we reference the most is the equator. But you can make you can make an infinite number of great circles. All right? So think of our sphere for a minute. If we had or excuse me, our globe for a minute. Okay, so you'll get a page of these, all of your own. All right, I know it's pretty exciting. What do we call these lines? We know this is the equator. What do we call these lines that go from pole to pole? Is it longitude or is it latitude?
I never remember which direction they go in.
I thought latitude was side, so it's longitude.
No, I remember longitude.
Okay, everyone take a look at your book. Longitude or latitude? Latitude go which way? Okay, they go like this, right? What is this thing?
That's longitude.
That is a longitude.
Yeah, because longitude, like long.
Okay? Now, your latitude lines, so this is longitude. We can't see that. Latitude. I've heard some students talk about latitude. They're like, look, it's like a ladder. You know, they're like steps on a ladder. Yeah, well I just got paid for that by AT&T. Okay?
Advertising.
Thank you. All right. So we've got our lines of latitude. And we have our lines of longitude. Now, which one, longitude or latitude, is a great circle? Okay, both includes one great circle, right? How many great circles are here?
Infinite.
4, 5, and 6.
1, 2, 3, 4, 5, 6. Everyone agree there's 6 great circles? Hey, stay with me, guys. Are there 6 great circles right there?
Yeah.
Yes, but
What? A great circle does what? Emma? It cuts it in half. So are these great circles?
No.
No. How many great circles are there?
One.
1. Okay. These are not great circles. Okay? There's one great circle. It's the one that cuts it in half. This is a great circle. In fact, how about this line of longitude? Is that a great circle?
Yes.
Yeah.
Well, it's
Yes,
the
because
same
it's
point.
splitting it.
It's from the same point.
Yeah. You can have an infinite number of great circles longitude. Like if you think of your lines of longitude, every one of those is a great circle. There's only one line of latitude that's a great circle, which is our equator. Okay? All these other ones that don't cut the sphere in half are not great circles. Okay? Yeah.
How come longitude can have an infinite amount? If you just turn it sideways, then it just turns into that.
Right, except for we wouldn't call those lines of longitude anymore, right? So I'm thinking on our globe, what we define as a line of longitude.
Yeah, but why do you have an infinite amount of longitude, but you don't?
So are you saying if I turn it like that?
Yeah, well, yeah.
Okay, so
It's from the same point. That's the difference.
it still has to cut it in half, though. Right, you have to be able to cut the sphere in half. So another way to think about it is this and this would intersect at the poles. Okay, they intersect at the top and the bottom. Okay, whereas these don't. They don't intersect at the poles.
Yeah, so why does latitude have only one, but then you said that longitude has an infinite? Oh, wait, yeah,
By definition of a line of longitude, or excuse me, a line of latitude, like this is 0, 10, and so on. By definition of a line of latitude, these are not great circles. By definition of a line of longitude, these are great circles.
So any one of those?
Any one of these is a great circle.
And then you have the top poles, and then the longitude ones, and the latitude ones are different layers of the circle, but the longitude ones meet at the points. So that means they're just like orange fields, like all orange fields are the same size. No, they're not. Ish. But if you have like a spherical cake and you cut it into layers, the layers are different sizes.
All right.
Good lesson.
Okay. Hey, okay.
Wow.
Let's move on. I'll come and help you when we start putting the rubber bands on there. Okay, postulate 7.3. Everyone take a look at page 394.
It's like way
394.
higher.
Am I fired?
Turning the pages.
Okay, volunteer to read postulate 7.3. So, yes. Allie.
Through a point not on a line, there is one and only one line parallel to the given.
Okay. Through a point not on a line, there's one and only one line parallel to the given line. That is Euclid's parallel postulate. Okay, so in other words, if I have a line, guys, I need you quiet, please. If I have a line and I have a point not on that line, in planar geometry, we say there's only one line that can go through this point that would be parallel to this line. And most of you know that. You're like, yeah, you have a line running like that, and they're parallel lines. It goes through that point. Okay? In spherical geometry, however, two lines will always intersect. But if we define a line as a great circle, two lines are always going to intersect in two places. Okay? In spherical geometry, two lines always intersect. Therefore, there are no parallel lines. There's no such thing as a parallel line in spherical geometry. You can't have it. They will always intersect. So what I want you to do right now is take your tennis ball, and I don't want you to necessarily take my word for it that there aren't any parallel lines. I mean, take your tennis ball and try to use the rubber bands to make two parallel lines.
I got this.
Okay? If you can do it, then we have disproved the spherical geometry parallel postulate, and we are all going to be very famous. Yeah, I think so.
Like this. Can you just do like this?
Okay, give it a go. All right, some valid questions. The question is, if I have this line, which we all agree is a great circle, okay? So I have that line, and that's like our equator. Okay? So a valid question that comes up then is, well, if that's a line, then what do I call like the line that cuts through those 2 points? Okay? I know. Now let's turn it like that. There. That way it doesn't look. Yeah, I know. Hey, you guys with me? Okay, so a bunch of you had that question. That's a good question. Okay, the reality is the way we deal with that on our globe, the way we handle that, we say, well, we call these lines of latitude. And we have another that, it's hard to keep the rubber band on there. Okay? You guys are going to make it tough to get to our lesson or to our assignment today. Okay? All right. So we call them lines of latitude, and obviously this one doesn't make a great circle the way we have it on our globe. Okay, I can't keep the rubber band there. You guys understand that?
Yeah.
However, the reality is, if we were trying to find the distance between those 2 points on our globe, what we would do is we would figure out what are the arc of what great circle that is. Okay, so we would form, using math, we would form a great circle that intersects those two, which then gives us a two-dimensional circle, which we could find that arc length, which we've done in chapter 6, right? So what you did in chapter 6, I know a lot of you are like, when am I ever going to use it? I mean, I'm going to never use this. Well, you're pretty happy that our planes can use it, because that gets you from Seattle to wherever you're going if you're on a plane. Otherwise, you're like, well, I want to go to I don't know, I want to go to Dallas, and you go from here, you're like, well, I'm just going to plot my point, okay? And you use Euclidean geometry, you don't end up in Dallas. You end up like, who knows where? You know, maybe you're in Nebraska somewhere, or who knows? Yeah.
It's like because the Earth is like curved, right? So if you make a line like this, straight line like this, and straight like that, but when you curve it, it's curved.
Yeah. Yeah, it's because the surface of the Earth is curved. Okay, so it's a different length. It's a curved length. Okay. The spherical geometry postulate, through a point not on a line, there is no line parallel to the given line. That's the spherical geometry postulate. Okay? All right, another thing. I want you guys to just read this real quick. Let you guys check that out. A little different. In spherical geometry, the sum of the measures of the angles of a triangle are greater than 180. Okay? The way you make a triangle in spherical geometry is you take your great circle, okay, and you have to intersect that great circle with two other great circles. So if I have, I mean, it's really great, yeah. So there's one intersection. Okay, and then if I take another great circle, maybe like so, okay, and now I have a great circle that has a right angle here, one that has a right angle here, and almost a right angle up there. So you're always going to have at least two right angles. There's your triangle. Okay? So one right angle, and this angle could be right, it could be a 10 degree, it could be 30, it could be 100, it could be a huge right angle depending upon how you form that last great circle. Okay, so there it just got wider, it's still 90, 90, and up here it's greater than 90 now.
1, 2,
Okay?
3, 4.
So the sum of the measures of a triangle are greater than 180. In fact, here's a summary of all of our comparisons between Euclidean and spherical that we talked about, besides one. The last one would be, like if we want the surface. The surface in Euclidean is infinite, whereas in spherical it's a finite surface. Okay, the surface area is finite, versus in spherical it's infinite. But number one, given a line L and a point P on line L, there exists only one line parallel, versus in spherical, no lines parallel. So what I've given you is I've given you this sheet where I spelled spherical wrong. Okay, I don't know why. We can add the H. There we go. Okay, number one, this is property one. You need to know these for your test. Given a line M and point P not on line M, there exists only one line parallel. Okay, and maybe you draw an example. There's line M. There's point P. Okay, there's only one line that's parallel to line M. You probably want to draw a better parallel line than I did, but there we go. Versus in spherical, there's no line through P parallel to L. Okay, so if I once again had my line, maybe I use my equator, my great circle there. That's my line on a sphere. And maybe point P is like the North Pole. There's no way to actually draw a line parallel to our equator going through our North Pole. Or even going through Seattle. Like if we put, well, here's Seattle. Okay? We're below the North Pole. There's no way to go through that point making a line parallel. It's not possible because it wouldn't be a great circle otherwise. So if you think, well, I could do it this way, I can make a line of latitude. Remember, that line of latitude is not defined as a line on a sphere because it doesn't cut the sphere in half. So whatever description you have to give yourself to remember that, it's important there.
I do not like this lesson. It's gonna be hard to remember.
You can do it.
There's just so many.
This is supposed to be number 2. I punched out number 2, unfortunately. I know. Unbelievable. Cheese is for sure.
You also punched out the H in circle.
Number 2. Very funny. Number 2, the sum of the measures of an angle in a triangle. How about on a plane? What do we have?
180.
180.
Good, 180.
What was that?
Okay, they add up to 180 degrees on a plane. On a sphere, well, they have to be greater than 180. So if I have that one, I can make a triangle going, I'm going to once again use my pole up there. It's going to intersect at a right angle. All our lines of longitude intersect the equator at a right angle. So maybe I automatically have 180 right there. It does not even counting what this is. This could be 1 degree up here. And I'm still at 181 degrees. Okay? The sum is greater. Greater than 180 degrees. Maybe this is 30 degrees. Who knows? You can put whatever you want up there.
1 trillion.
Number 3, 2 distinct lines intersect at most 1 point. So if I have that line and that line, they're distinct. They intersect right there. They'll never intersect again on a plane. However, on a sphere, 2 distinct lines, I'm going to use my most popular line there, the one every other line strives to be. Okay? There's our equator again. Another line, let's say a line going this way.
Line goals.
Okay? It's going to intersect right here. So it'll intersect right there, and it'll intersect again back there. Okay, so it has 2 distinct, at least, or excuse me, it has 2 distinct points. And you can demonstrate that on your globe there. You got the whole tennis ball in your hand. Okay? Next one, number 4. Through 2 given points, there is one and only one line. So if I give you this point and this point, there's only one way for me to form a line. There's no other way to draw a line through those. On a plane, or excuse me, on a sphere, if I give you that point and that point, how many lines can you go through there?
So many.
Yeah, like tons, man. Tons. Well, mathematically, that's only 2,000. Okay. Well, more than 1 ton, I guess. Multiple 2,000s.
Multiple
Okay,
times.
and we're dealing with pounds. But let's say an infinite number. Okay, so maybe I have that one, and then I switch to an amazingly cool color. Cool. Oh, I know. Okay, pretty cool. I know. Okay, you have that one. You have all these lines that slice up. Okay, you guys have kind of demonstrated that with your tennis ball. There's 2 lines. You could put a 3rd line like that. Okay, they intersect at the poles. Infinite number of lines will intersect at the poles, cutting that circle in half. Or if you think of an orange, like orange slices. Okay? This would not be the kind of orange you want to eat. It's a little probably chewy. Okay? I know. Yeah. All right. And not orange. You know. All right. The shortest distance between 2 points is the length of a segment. Okay? Sorry, 1 line here.
The diameter would be the other
Okay, the arc, in this case we talked about it. If I have these 2 points, the shortest distance on a sphere is the arc of a great circle. From any 2 points, if I want to go from Seattle to Texas, through those 2 points, there exists an arc of a great circle. Okay? You should be able to attach these 2 points using the arc of a great circle. Always. Okay? And we kind of saw that on our sphere here. Okay? Where we have these 2 points, and we can put this line through them and make the arc of a great circle. You can do that at any 2 points. Okay? It's the arc length of a great circle. Sorry, arc of a great circle. Okay. Any questions there? Those are the 5. If you want to add 6, you can talk about the surface is finite. You can draw your picture if you want. Infinite. All right. And you may find some others that we talk about or when we watch our video tomorrow. It's brought to my attention, I switched these. Unbelievable. Good thing you guys are thinking. Infinite and plane, finite on a sphere. Ridiculous, I know.